Okay, so for this section, we're going to deal with the log properties, and I think it's worth your time, uh, perhaps, to go out and watch what Sal does out in Khan Academy about the proof to derive these properties. I got links in that flipped classroom page, and I think it's worth your time. It won't take too long. You can always watch it on double speed if you want. All right, so these are the three log properties that we're going to examine and we're going to look at. We're going to use that's the sum property. It's the difference property. So when you're having sum, you multiply the two arguments. When you have a difference of two logs, you divide the two arguments. And if you have something in front of a logarithm, you can get rid of it, get it away from in front of the logarithm by writing it as an exponent. And it's true. I'm sure you've seen these in college algebra or algebra 2. So now they're telling us this. They want us to expand this log expression. When you in Calc 2 is when this really comes into play. That's when I've seen it, where I had to use it. It made my life easier. Before that, it's just kind of it helps you solve equations. It helps you expand things out. It's just part of the algebra you need to have some mastery of. So I see a division. I see a couple of products. I see a product there. I see some exponents. So because I've got that division first, and I want to kind of get rid of that fraction, and I know that log property, when I divide two things, that's the same as subtracting the two logarithms. So I can write this way. I can write log 5x squared, and squared, Dan, not 2. I mean, not 5. And I guess I'll put those in. What the heck am I doing? A minute here. Let's move some stuff around. Here we go. So squared. I'm going to put that in parentheses. Minus log of y to the fourth. So do you see how I put the numerator first minus log of the denominator? And now we're going to do a little more expansion. Now I see a product. So I'm going to write that as a sum. So log base 10 of 5 plus log x squared. And let's work at this other one. I see an exponent, so I can write that down in front of the logarithm. So 4 log y. Now I'm going to do that same thing here. Well, log 5 I can't do too much with, but I can bring the 2 down in front. And then minus 4 log y. So I guess that's about as far as we can take it. I don't know that we can take it any further. So they're all linear. So that's expanding it. Now, where this comes in easier, now it's easy. The calculus behind this is easy, but you don't need to worry about that this year. Now they want us to do the reverse. I've got a couple of these that I want to do with you. This one's not too bad. I know I see I see a sum, so I know I'll be able to do some multiplication, but I also see that I've got an exponent in front of those, and that's kind of problematic. So we're going to get rid of them by writing them as an exponents. So I'm going to write this as log of x squared plus log of y to the third. Now this is true. All these examples I've been showing you so far is log base 10, but they could be log base anything. It's just that common log. So then, because I've got the sum going on, I can multiply the two products. So I can write this as log of x squared y to the third, and I'm done. I got a single logarithm. So here's a couple of other ones that are there's some twists here that I wanted to make sure you saw them before I turned you loose. At least to see a video on them once. In my Open Math, they have these videos, associated videos. But so I see a bunch of coefficients here. I want to kind of get rid of them. So log 6z to the fourth plus log base 6 of x to the fourth. And I'm going to leave that minus sign there. I mean, I could bring it up. It wouldn't be wrong to bring it up. I'm going to leave it there because it's going to emphasize a point I want to I want to do. So log y squared. And so now what I see is I see a sum. I see a difference. So I know this has to be in the denominator. So I know it's going to be log base 6. And then I know I'm going to have a fraction because of that negative sign. And I've got a z to the 4th times x to the 4th. So I'm going to write those in alphabetical order. Not that it matters, but... And then the y squared goes in the bottom. And we took this gnarly looking mess and wrote it as a fairly compact, let's put a parenthesis here on it, I guess, log expression. So that's how that works. Maybe we should go back and talk about what would happen if I brought that negative up front, because it doesn't matter. It's the same math. Let's see if I can do some deleting. I don't want to delete all that. Here, let me do some erasing then. Yeah, stuff's not too bad. So what if I make that plus and minus? So I bring that negative 2 up. Well, now I see a whole bunch of products, right? So log base 6 of z to the 4th times x to the 4th times y to the negative 2. I know when I have a negative exponent, that means I need to kick it downstairs, or I need to take the reciprocal. I need to get it in the denominator. So do you see how I'm going to get the exact same thing? I'll rewrite it as x to the 4th, z to the 4th. Then the y to the negative 2 comes downstairs. So see, it doesn't matter where you deal with that negative. It's just sometimes it's easier to leave it there. So that's that one. So for this one, do you see how I've got the double negative? I could deal with those exactly the same way. There's a couple of ways to deal with them. Let's deal with it the last way, where I brought the negative on top. Maybe that'll help. So I'm going to get rid of those get rid of those coefficients, write them as an exponent here. So log base 6 of u to the 24th plus log base 6 of v to the 6th plus log base 6 of w to the negative 6, and negative 6. So then we could do that same kind of deal. I don't know if you remember that from the last video, or the last problem. I went u to the 24th, v to the negative 6, w to the negative 6. And I know this is going to be a fraction, so that's why I drew that fraction sign a little ahead of time, I guess. That fraction bar. Those get kicked downstairs. So v to the 6th, w to the 6th on the bottom. And I guess I should probably clean that up a little bit, but I won't. Here, I'll do that. Okay. So that's how you deal with the double negatives. You can treat them separately. If that doesn't work for you, you can think about it this way. And sometimes, the reason I want to talk about these other ways is sometimes it's easier to look at it another way. You can do more with it, or not more with it, but do it more quickly. What if I do this? What if I factor out, what if I pretend this is 24 log base 6 of u, and I factor out a negative. What if I just factor out the negative? Let's keep it easy. 6 log base 6 of v plus log base 6 of w. Well, I see there's a subtraction sign there. Well, first off, it might be nice to write this as a single log. Is there 6 here? I lost a 6. So those get kicked up as exponents. So can I write this as log base 6 of v to the 6, w to the 6? Are you okay with me making that jump, I hope? Actually, let me get rid of those parentheses. There's this, have that minus sign, and I have that log base 6 of u to the 24th. Now I have the difference, 2 logs. I'll write it as a quotient. So log base 6 of u to the 24th over v to the 6th, w to the 6th. So I don't know if that's any easier, any quicker, but it's a different way to look at it, okay? I do this, I selected this question because I know when I was learning this stuff, these double negatives were problematic. I didn't quite know how to deal with that, so I wanted to make sure you saw that. So now we're going to apply these properties to solving log expressions. If you remember back in section 3, we were rewriting logarithms as exponentials and to solve them. Nice trick. It makes it really easy. But that only works if we have one logarithm. So it would be really nice to condense this into a single log. So I see a subtraction sign. So that means I'm going to write this as log of x plus 5 over x, and that equals 2. Now, to me, that log is problematic. I know that this log is log base 10, so I'm going to rewrite this so it's no longer a logarithm. I'm going to rewrite it as an exponential. Remember, it's the base raised to the power equals the argument or the answer if you've listened to my other videos. So that can become 100 over 1 equals x plus 5 over x. Now it's just a proportion. We'll do the cross products. 100x equals x plus 5. 99x, right? Subtract x. 99x equals 5. So x equals 5 over 99, which is not a very nice number. We could go graph it and check it out. I certainly don't really want to plug that in to check it, but we certainly could. I mean, that would probably work, okay? So here's another log equation we're going to solve. So it's a product, so I'm gonna multiply the two arguments. So log, I'll write it 10 there because this is base 10, times x plus 3 equals 1, and then get rid of the logarithm. So x times x plus 3 has to equal 10 to the first power. And I hope you see, this is a quadratic equation. So it's going to give me x squared. And so when we solve quadratic equations, right, we set them equal to 0. And then try to factor it. And if that doesn't work, we're going to use the quadratic formula. Fortunately, I think this factors to x plus 5 times x minus 2. That way I get the negative 10 and the middle is positive 3x. So that tells me x could be negative 5 or x equals positive 2. Now, remember what I said about watching out for extraneous roots? Well, we can't take the log of a negative number. So if I were to drop the negative 5 into this, I would get log of negative 5, log of negative 2. I can't do that. That's an extraneous root that resulted from our algebraic manipulation here. So, as you'll see when we start doing identities, you only want to work on one side because you don't want to introduce extraneous roots like this. Because that's what we did. Our algebra introduced those. Okay, so make sure you look for extraneous roots. That's I'm going to ask you a quiz question like that. Okay, then we come to these kind of things. And these kind of require a paradigm shift in a way. So I would really like to have x's on the same side. I get these exponents. So what if I do this? What if I divide both sides and get the x variables on the same side? So what if I divide this by 2 and this by 2, and I divide this by 2x, and not 3x, 2x, and so this by 2, and this by 2x. I'm bound to determine to write 3x, aren't I? So that gives me 3 over 2. The 2x over 2 to the x cancels out, equals 4 to the x over 2 to the x. Now, this is tempting just to cancel out the 4s, and technically we can, but what if it's a more gnarly decimal or fraction base? So the way to think about this is, this is 4 over 2 raised to the x. Because remember, if I have a over b raised to the x power, the exponent property says I can multiply. That's 1. That's a to the x over b to the x. And I can just go backwards and rewrite that. So what's nice about this is now I've got 3 over 2 equals 2 to the x. I'm going to write that as a logarithm. This is what we did last time. So log base 2 of 3 over 2 equals x. And then we can just use a change of base, right? The log of 1.5 over log 2 and get a decimal value. Okay. Maybe I'm not convincing you that this is the way we want to think about this. So I'm hoping the next question will give you a way to deal with that. Okay, so they said we've got a population here. Why don't we just say, I'll say A equals, let's see, initial value is 1,000, and it's continuous growth rate. So continuous means it's e to the kt, right? So e to the 0.06 t, and then we got town B. It starts at 5,000, but it's decreasing. Oh, it's decreasing in the annual rate? Let me do this. It's doing a couple of things here. Let's do it. Let's keep it. And we'll do it. The one I'm going to give you is not going to be this complicated. But let's annual rate. So if it's dropping, it's decreasing, we're doing that y equals AB to the t in this case. And this was AE to the KT. So here's the annual. Remember, B equals 1 plus the rate. If the rate's negative, we're going to write 0.95 to the T. Alrighty, so I know we want to know when will they be equal. So aren't we setting these two equations equal? One thing that's problematic for me is the 0.95 and the e to the 0.06. So it would be nice if they were the same base, either continuous growth or annual growth. And one thing you can do, and you've already learned how to do this, is how to change continuous growth to a annual rate and vice versa. So maybe for this question, I'm going to do this a couple of ways for you. Maybe for this question, I see if I wanted to change this equation so it's an annual rate, won't that be 1,000 times b to some power? So the only thing that's different here, remember, is the b and the e to the 0.06. Those have to be equal. So we could just grab a calculator. Here, I'm going to grab my calculator here. And I'm going to do e raised to the 0.06. I'm getting 1,000 times 1.0618, I'll go with, to the t power. And that has to equal 5,000 times 0.95 to the t power. Now, just like that last question, it'd be nice to get these on the same side. So I think what I'm going to do is I'm going to divide 5,000 by 1,000, and I'll divide by 0.95t. So one here, let me move this up a little bit, see if it'll let me move the whole mess up. Oh, it will. So I'm going to write 1.0618 to the t power divided by 0.95 to the t power equals 5, right? Because it's 1,000 divided by 1,000. And then we'll treat this so we only have a single variable. So we're going to raise the whole fraction to the t power. And then this is the decimal. I can calculate that decimal. Well, what is that? It's going to be divided by 0.95. So I'm getting 1.1177-ish to the t power equals 5. Now let's just rewrite that as a log. So log base 1.1177 of 5 equals t. And then you can just choose change your base, right? Log of 5 divided by the log of 1.1172-ish. 72-ish. So what is it? I get the log of 5. Let's see. So log 5 divided by the log of that answer. I'm getting t equals 14.46 years. So during the 15th year, right? So here, I'm going to write that down somewhere so I don't lose that, because I want to go back and show you what if we used a different form. Here, it's not letting me delete things here. I'll just delete all this. 14.4 here. Because sometimes what happens is they're going to give us, remember I was a little confused here at the beginning of the way they switched annual and continuous. What if they had done this both as continuous? And I don't have an example like that, so we'll have to, here, we'll just wing it here. Sometimes you're going to get both of these. Let's solve this as if this were also continuous, all right? I think this is worth watching it, so watching for your time. So I'm going to get town A. Town A is going to have, 1,000 times e to the 0.06t. And if it's dropping 5,000, e to the negative 0.05t, right? Because if it was continuous. So then if we tackle it the same way, I'm going to divide by 1,000. I'm going to divide by the e to the negative 0.05t. So that gives me e to the 0.06t divided by e to the negative 0.05t equals 5. This is where people have a hard time with this. So, but we can do that same thing where we're going to do e to the 0.06 divided by e to the negative 0.05. And that's all raised to the t power. Okay, and what is that equal to 5? So then we can do the same thing. Grab our calculator, e to the 0.06, e to the 0.06 divided by e raised to the negative 0.05. I'm getting 1.1, what am I getting? I'm getting 1 point, a little bit different number, but not much. I'm getting 1.116. 3 I'm going to round to. See, remember the other one was 1.117? I think that's because of my rounding. To the t equals 5. And then we can do the same thing, right? We can rewrite it as a log and then do log of 5 divided by log of, use the change of base formula. And I think we're going to get pretty darn close to the same thing. Let's see. So I want to do log 5. Let's see. Divided by the log of that answer. Oh, nope, Dan LeMay messed up. Here, just a minute here. I raised it to a power here. Log 5 divided by the log of 1.1163. Yeah, I'm getting 14.6. 14.6. What was the other one? 14.4. So still during the 15th year. So, all right. So this is the twist I wanted to make sure you see. That comes up in the exercises.